Good morning, everybody. Today we're going to be talking about the rate of decay of a radioisotope. We've already talked about the mode of decay, and now we're going to talk about the rate, which is something called half-life. So the rate of decay of a radioisotope is called its half-life, and we can find that value on table N. So half-life is the amount of time needed to get half as much. You could sort of think of it like the amount of time that something remains. So if I drink a cup of coffee in the morning and I have caffeine in my system, it's not like all the caffeine stays for 12 hours, and then at the 12th hour, every bit of caffeine suddenly disappears. The caffeine is metabolized by my body at a pretty consistent rate. So at any point during the day, you could test my bloodstream and you'd see that a percentage or a fraction of the original amount of caffeine remains. And that's pretty much what's happening with our radioisotopes. If we start with a given amount, over time, as it decays, we'll be left with a certain amount. And to quantify that, we measure it in terms of half-life. So the amount of time it takes for a radioisotope to decay so that only half of the original amount remains. So let's just look at that really quick. So if we start with a 100-gram sample of anything, the half-life would be the amount of time for there only to be 50 grams left. And if that isotope goes through another of its half-lives, so if that amount of time passes again, there'd be 25 grams left. And then 12.5 grams left. And then another half-life would result in there only being 6.25 of the original sample left. And then another half-life would result in 3.125 grams left. So this represents 5 half-lives that have passed. And for any isotope, if we started with 100 grams and there's 3.125 grams remaining, that means that 5 half-lives have passed. So one half-life of any isotope will result in 1/2 of the original amount remaining. 2 half-lives means that there's 1/4 of the original amount remaining. 3 half-lives, we're left with 1/8 of the original sample. 4 half-lives, 1/16. 5 half-lives, 1/32, and we could go on and on and on and on and on and on and on. But for this class, we only will need to calculate up to 5 half-lives. Okay, so how much time does it take for one half-life, for the radioisotope to decay by half? Well, the rate is different for different isotopes. So if we look at carbon-14, one half-life takes 5,715 years. But for calcium-37, it's 182 milliseconds. And for uranium-238, it's 4.51 billion years. So that's crazy. So if we look at carbon, for example, one half-life takes 5,715 years. Another half-life means that another 5,715 years has passed, which is a total of 11,430 years. Let me put my units. If I have an original sample and only 1/8 remains, well, that means 3 half-lives have passed. And for carbon, that's 7,115 years times 3, which means that for 1/8 of the original sample to be left, if this is carbon-14 decaying, that would take 17,145 years. All right, so let's just look at some example problems. This might sound confusing so far, but the calculations are really simple. All right. So in any problem, you might be given the initial amount of the radioisotope or the fraction remaining. So they might give you the grams that remain, or they might use an actual fraction and say 1/2, 1/4, 1/8, 1/16, or 1/32 remains, which correlates to 1 half-life, 2 half-lives, 3 half-lives, 4, or 5 half-lives have passed. So they might give you initial amount and fraction remaining and ask you to determine the half-life, or they could give you the half-life and the initial amount and ask you what fraction will remain after a given amount of time. Let's just do some problems. Keep talking. So, first one. What's the number of hours required for potassium-42 to undergo 3 half-life periods? Okay. If I check the reference table, potassium-42 has a half-life of 12.36 hours. So to go through 3 half-life periods, it's simply 3 times 12.36 hours. 3 times 12.36. 3 times 12.36. Is about 37 hours. So that means that whatever amount of potassium-42 we started with, after 37 hours, 1/8 of the original sample would remain. Because 1 half-life cuts it in half, 2 half-lives results in 1/4 of it remaining, and when 3 half-lives have passed, only 1/8 of the original sample remains. So now let's do another problem. And the basic equation that we can use, if this helps you, is that the total time that has passed over the half-life of the radioisotope is equal to the number of half-lives that have passed. And of course, we can just put that over 1. So let's use this equation to help us solve problems. If you can do this stuff in your head, which you probably can, you don't need the equation. But if you're not a math person and you'd like to have an equation to work with, use the equation. So here we go. After 32 days, 5 milligrams of an 80 milligram sample remains unchanged, or just remains. So that means that 75 milligrams have decayed and 5 milligrams remain. What is the half-life of this element? Okay, let's plug it into my formula. So the total time is 32 days have passed. I want to solve for the half-life, but I need the number of half-lives so that I can cross-multiply. So if I started with 80 milligrams and 5 milligrams remain, well, how many half-lives is that? Well, half of 80 is 40, half of 40 is 20, half of 20 is 10, half of 10 is 5. That is 1, 2, 3, 4 half-lives have passed. So 4 half-lives. And now I just simply cross-multiply. 4x equals 32 days. This element has a half-life of 8 days. Okay, let's do another one. If 1/8 of an original sample of krypton-74 remains unchanged after 34.5 minutes, what is the half-life of krypton-74? Okay, total time is 34.5 minutes over the half-life of krypton, which is what I want. And I need to know the number of half-lives to solve this, and they said that 1/8 remains. So don't forget, after 1 half-life, half remains. After 2 half-lives, 1/4 remains. After 3 half-lives, 1/8 remains. So that means that if 1/8 remains, doesn't matter what sample we're looking at, 3 half-lives have passed. Okay, so 34.5 divided by 3x, if I cross-multiply, 34.5 divided by 3 is, oops, did something wrong, 34.5 divided by 3. Oh my goodness. Is 11.5 minutes. So it has a half-life of 11.5 minutes. So that was 3x equals 34.5 divided by 3 divided by 3. Okay, let's do one more example. How many days are required for 200 grams of radon-222 to decay to 50 grams? Okay, how many days are required? So don't forget, total time over half-life equals number of half-lives that have passed. I want the total time that has passed. And I need the half-life of radon 222. So I'm going to go to my reference table, and I'm going to look up radon 222. It has a half-life of 3.823 days. I'm just going to say 3.8 days. So its half-life is 3.8 days. And to solve this, I need to know the number of half-lives that have passed. So I started with 150 grams remain. Half of 200 is 100, half of 100 is 50. That means that 2 half-lives have passed. So 2 half-lives have passed. So that means 2 times 3.8 is going to be equal to X. So 7.6 days are required. And if you want to go take the pod, take the pod. I'll do one more example. Sorry, this is taking so long. What is the total mass of a 10-gram sample of potassium-42 that will remain unchanged after 12.4 hours? Okay, the total mass. So once again, my formula is total time over half-life. Total time over half-life equals the number of half-lives that have passed. Actually, I don't even really need that. So potassium-42, let's just go get its half-life. Potassium-42, we said, has a half-life of 12.36. So the half-life is 12.36. So that's 1 half-life. So if I started with a 10-gram sample and 12.5 hours have passed, 1 half-life, 5 grams. That's it. So 1 half-life has passed. We don't even need this. I mean, we could plug it in, but that's just ridiculous. And that means that 5 grams of the K42 would remain. Okay, go do the pod. It's just a couple questions just so you can practice. And any questions, message me.